Where's Mr. Sams? He's gone. What happened to him? Oh, I know. Maybe I can make him appear somewhere if I use the gong. I'm looking. Where's Mr. Sams? I don't see him. Where is he? There he is, Mr. Sams. And here he is again. Oh, how did he get there? And he's back. How did you get from there to there? Ah! How did you get there?
Quantum mechanics.
Quantum mechanics?
Yes.
Like it's like you were there, and then you were...
Somewhere else. Yeah. But never in between.
But you were never in between?
No.
How'd you do that?
Hey, the power with the gong.
Yeah, well, we have the gong with us today.
Yeah.
It's pretty cool. Yeah.
And the gong mallet. That's a beefy mallet.
Don't hit me with that.
Hey, used as a weapon.
Ah!
Alright.
So, hey, what are we talking about today? Quantum mechanics.
Yeah.
Mr. Sams appeared in various places around the room and used the power of the gong.
Oh, yes.
And it's very powerful. Yeah. So we're going to talk about quantum mechanics today. So I guess we should get at it, huh?
Yeah.
All right. Hey, big question today. You know, trying to figure out where is the electron in the atom?
Where's the electron? It's kind of like Where's Waldo, but with electrons.
Yeah, where's Waldo, or what was the other one? Carmen Sandiego.
Oh, yeah.
Where's Carmen Sandiego? Yeah, it's kind of one of those things.
Is that game still around?
I have no idea.
I played that when I was in elementary school.
I taught
Version 1. You taught with it? He's old.
I've been old none. Okay, so where's the electron in the atom? That's the question today. Okay, and the answer, of course, is really simple, right?
It is. We don't know.
Actually, the answer, that's really the answer is we don't know.
It's a very easy answer.
But the answer, actually, I say, is somewhat complex. Because we can't actually exactly say where the electron is. We can only say where we think it is. Probably. Probably be?
Probably, yeah.
How about likely? It will likely be. I think that's the word I was looking for. Likely be. We can't actually know exactly for certain where the electron is.
No. And when we define these orbitals that we're going to talk about, we usually talk about in terms of 90%.
It's the 90%.
Where is it likely to be 90% of the time?
Yeah. Hey, this is developed by a guy named Werner Heisenberg. He was, and Louis de Broglie, and Erwin Schrodinger. Did I say that well?
Yeah, that was nice.
Yeah,
I like that.
Schrodinger.
Nice rolling
De
R.
Broglie and Heisenberg. Kind of like the Hindenburg, right?
Not quite.
Not quite.
No.
All right, sorry, we shouldn't make fun of these very, actually, brilliant people.
Yes.
They were amazingly brilliant.
Yeah, much smarter than us put together.
Yes, indeed. All right, and this is this dude Schrodinger.
Yeah.
I actually need the umlaut over the top of his name. So the Schrodinger made an equation from the hydrogen data. Do you remember the hydrogen data?
Yeah, that's the stuff that Bohr put together, right?
Equals negative 2.178 times 10 to the minus 18th times z squared over n squared.
I remember that.
So he did all that stuff, and he came up with some answers.
Yeah.
And you know what he got? You know when you do like math and you come up with an answer, an equation? Usually that's a
line?
It's a line, but guess what? He did not come up with it. His answers were actually shapes.
Interesting.
And those shapes were actually not solid shapes. They were like hollow, but they were, we call them probability distributions. Now that makes a lot of sense, doesn't it?
Oh, of course.
A probability distribution.
Yeah, it's where something is probably.
Yeah, well, with 90% certitude.
Yeah.
Now, the math of this, actually, let's back to talk about that. The math of this is very high.
Yes.
It's like advanced calculus.
Plus some.
Actually, uber advanced calculus. Is that the word, uber?
I think so, yeah.
Okay, uber advanced calculus. Now, have our students had calculus?
Some maybe.
No. Uber advanced calculus?
Probably not.
Probably not. So, the good news is...
We probably haven't had enough math to do that either.
We're not good enough with the advanced calculus ourselves, so we like that Mr. Schrodinger solved it back in the 1920s.
Yep.
And these are the answers.
Yeah, I like pictures.
We get a picture.
Yeah.
So, there are different shapes. Now, the shapes are called orbitals. Now, that is a residual of Mr. Bohr's model, where he thought that the electrons orbited the planets like, orbited the nucleus like planets orbit the sun.
There we go.
That's what I was trying to say.
I know.
But the reality is they don't orbit nothing.
Nope.
They exist in shapes. And so if we look at this shape, which is called the S shape, which stands for spherical.
Sphere.
There are different shapes. So the 1s shape right here, there's the 1s shape, and that's an S, same shape, it's bigger. And there's the 3s shape. And actually, we should actually visit about this. This right here, if I were to look, let me change colors, I think that'll be better. The 1s shape is a solid, not solid, it's a hollow sphere. And then the 2s shape, most likely it is in this area right here, but there's also a probability that he could be inside here. But he couldn't be in between here where the white space is. And those are called the nodes.
Right.
So you might have remembered back if you took last year's class and if we talked about it, that we had these spherical shapes, and we didn't talk about the nodes.
No.
Advanced topic here, ladies and gentlemen. There are nodes.
Right. There are places where it can be and where it can't be, kind of like me when I was popping around in the classroom earlier.
Yep, indeed. Okay. Now the second shape are called the P subshells, and they look like this. Somebody used to say they look like a dumbbell, like Arnold Schwarzenegger lifting weights.
Did you just call Arnold Schwarzenegger a dumbbell?
Well, maybe so. He wasn't always the smartest guy, but I guess he's governor or something.
He is
now.
governor of California.
Yeah, at least
he was my governor. He signed my teaching credential. Well, his copy of his signature is on my teaching credential in California.
So they kind of look like a dumbbell.
Yeah.
I'm not sure I'd call that a dumbbell. But anyways, this is the P shape. And there's actually three different shapes. There's the one that's on the x-axis called the PX, the one on the PY on the y-axis, and the one on the z-axis. And this is sort of just a... And this picture right here, if you look at it, actually has like little dots. It almost looks fuzzy. It's as if it's a bad picture. But that's kind of a point here.
Yeah, there are no really defined edges of these. Again, we're talking about probability, where it is 90% of the time. So... we can't really draw a line if we're only certain about where that line is 90%. We're 90% certain about where that line is.
Indeed. Another thing that we should also make a note of that's kind of odd about this is that it's as if the electron is everywhere on the surface of this shape at the same time. And that's weird.
It is very.
How can a little particle that's itsy-bitsy be here and also here at the same time? And here, and here, and here, and here, and there. It just is. Actually, it has to do, frankly,
That's
folks,
back to the wave property.
the fact that the electron is a wave. Remember we learned that matter are both waves and particles in the last podcast. So it's the fact that it's a wave, and it's what we call a wave function. And actually, the probability pattern, if we want to get totally correct, is actually the square of the wave pattern. How's that for crazy? Okay.
That's crazy.
It is crazy. The third type of shape is the D shape. Looks like a four-leaf clover, if you ask me.
Except for the donut one.
Except for the donut one. I like the donut one.
I like donuts.
So these are the four-leaf clover ones on different axes, and this is a different shape. Okay? And lastly, actually, not lastly, but it is the last one I have a slide for, this is the F shapes.
Yeah.
And there are 7 of them, and I don't even know what to call these things.
Far out.
Far out. Oh, my good. Yeah, you go far out. There's actually G shapes. Did you know that?
I did, but I have never seen a diagram.
I saw a picture on the internet, and they were even farther out.
Farther out, like...
greatly far out.
Groovy?
Groovy out.
Ah.
There you go. Yeah, I get it.
I'm sorry, I'm trying to use some words that you might be familiar with.
Groovy, man. I'm way cool with that. Yeah.
He's old.
I'm old. Where indeed is that electron?
Well, we can sort of kind of know it if we know less about something else.
You see, there's this guy by the name of Werner, Heisenberg, one of those brilliant dudes. And he said, in fact, it's called the uncertainty principle because the idea is that you can never exactly know where the electron is.
Right.
So that.
The more you know about its location, the less you know about its momentum.
So there's actually an equation that relates this, and it's delta x times
delta
mv is greater than or equal to h over 4 pi. What in the world is that?
I don't know.
All right. Delta x is your position. How well do you know where the electron is within a particular number of meters, or centimeters, or nanometers, or whatever? And this is the mass of the object and its speed, because the electron ultimately is moving. This is, by the way, when you take m times v, it's actually called the momentum. And it's greater than or equal to h over 4 pi. And h, if you recall, is Planck's constant, and it is a very small number.
Yes.
10 to the minus 34th. And so what you can do is you can solve for, if you do the math, I don't know if do you want to do the math?
Nah, let's not do that.
If you do the math, what you're going to do is you're going to discover that the value for delta x is usually in the neighborhood of about a meter for an electron in an atom. Now, why is that a problem?
That's huge.
A meter is like 3 feet, right? And 3 feet is much bigger than an atom. An atom is, of course, in the nanometer range. And so the ultimate answer is, it's kind of like the old joke. if you ever go to you go to a hotel and they've got this sign on the front of the door. You ever been to those hotels and it says, George Bush slept here or Barack Obama slept here, one of those type of things? Well, they have Heisenberg slept here. Maybe.
Maybe.
Because it's the Heisenberg uncertainty principle, because you never know.
Right, because the more you know about the position, the less you know about the momentum. The more you know about the momentum, the less you know about the position.
So that's probably as clear as mud, frankly.
Yeah.
But the point is that you can never know the exact position of an electron. And if you did, it would have moved.
Yeah.
So that does create some interesting...
kind of like Mr. Sam's.
Yes, like Mr. Sam's at the beginning. So Mr. Sam's... Okay. We're going to use the white colored ink. Okay. Now the shapes come from a mathematical equation. Okay. Now I'm not going to write the equation, but it has variables. Okay. So in a mathematical equation, usually you have like x's and y's and such like that.
Mm-hmm.
Well, this has variables, and these variables are called
quantum
numbers. And what I really want you to realize is it's as if every electron has an address. Every electron has an address. Okay, there are 4 different quantum numbers, and the variables are L, M sub L, and Ib sub S. And each of these represents something else. N is called the principal quantum number. I'll use the number symbol to not have to write that down. L is called, L's got a funny name. It's called the
azimuthal.
A-Z-I-M-U-T-H-A-L. And that's the quantum number. And M sub L is called...
magnetic.
Oh, see, M for magnetic, yeah.
Yeah.
Magnetic quantum number. And M sub S is the...
spin projection.
We just call it the spin. The spin quantum number.
Yep.
Now, the reason we have a spin, by the way, is the fact that the electron is actually spinning.
Yeah.
So the individual little, if you think now back to the electron as a particle, it has a spin, kind of like the world spins on an axis, the Earth. And so these are the names of these, all right? And that leads us to this table that you actually probably have a little bit more filled out, but I left it unfilled on purpose for us to kind of talk it through. I think would be good. All right, let's change to a new color. All right. In the principal quantum number, of course, that is an N. And the value of N is somewhere, N is going to be 1, 2, 3, 4, ... It's an even whole number.
Yep.
Oh, an example, of course, N is equal to 1, 2, 3, etc. I guess I should have done that. That's fine. The azimuthal is, of course, the symbol is L.
Mm-hmm.
And this is, and actually this is the shell. We'll talk about this in a minute, I think, in another slide. This is the subshell. Actually, when you write subshell, I want you to write that this is the shape. Or you can say S, P, D, or F. And the number is always between L.
No, it's between 0 and N minus 1.
So it's 0 to N minus 1.
Yep.
All right, so if you have N equal to 3, L can be either 0, 1, or 2. Okay. All right, and I'll save a slide for that later. All right, and then M sub L is the energy shift, and this is always between negative L and positive L. So if L is equal to 2, M sub L will be equal to negative 2,
or
negative 1,
or
0,
or
1,
or
2.
There you go.
So there are 5 different options when L is 2. And the spin quantum number, which of course is M sub S, this is just going to be negative 1/2 or positive 1/2.
Yep.
All right, now I want you to think of this as an address for an electron. Okay, so let's kind of think this through. All right, so folks, what we're going to do, you've got this quantum number practice, and Mr. Sams and I just had a time out here, and we talked about that. I think we're going to do this after we do something else, so just bear with us. We'll come back to this. Leave it blank. We're going to put something there in a minute.